On October 9, 2022, a pulse of gamma rays struck Earth with such force that it briefly overwhelmed nearly every gamma ray detector operating in space and disturbed the electrically charged upper atmosphere far below, thousands of kilometers from where the light actually arrived. Astronomers now call it the BOAT, short for Brightest Of All Time, the most luminous explosion of any kind ever recorded reaching this planet. It began roughly 2 billion years ago and roughly 2 billion light-years away, with the death of a single massive star, a star that had already spent millions of years quietly shedding its own outer layers into space before its core ran out of options entirely. What follows traces that star's life, the extraordinary physics of how it died, the almost 2 billion years its light spent crossing an expanding universe, and the handful of minutes in 2022 when instruments across the planet all noticed the same impossible thing at once. Roughly 2 billion years before that pulse of light reached Earth, in a galaxy now sitting behind the faint stars of the constellation Sagitta, a single star was already living on borrowed time. It had formed with somewhere around 40 times the mass of the Sun, among the heaviest stars a nursery of gas and dust can produce, and from the moment it ignited, it was burning through its nuclear fuel far faster than a star like our own ever would. A star's mass sets its fate more than anything else about it. Heavier stars fuse hydrogen into helium at ferocious rates to hold up their own crushing weight, and this one had roughly 40 times the Sun's fuel but needed to burn it, perhaps 1,000,000 times faster, just to keep from collapsing under its own gravity. That furious pace burned through the star's hydrogen in only a few million years, a blink of an eye next to the roughly 10 billion years the Sun will spend on the same stage of its life. Once the hydrogen at its center ran low, the star's core contracted and heated further, hot enough to start fusing helium into carbon and oxygen, and layer by layer it kept doing this. Each time one fuel ran short at the center, the core shrank and heated until a heavier element could ignite in its place. The result, by the final years of its life, was a star built like a series of nested shells, hydrogen fusing in an outer layer, helium fusing further in, then carbon, then neon, then oxygen, then silicon, each shell burning its fuel and dumping ash onto the shell fusing beneath it. At the very center sat a core of iron, and iron is where this process stops being able to help the star at all. Fusing iron does not release energy, it consumes it, so an iron core cannot generate the outward pressure that has held the star up against its own gravity for its entire life. Long before the core reached that point, though, the star had already begun losing itself. Stars this massive drive intense outward winds, streams of charged particles blown off the surface by the star's own furious radiation, and over its lifetime a star like this one can shed more than half its original mass back into space, sometimes far more. By the time it neared the end of its life, this particular star had likely lost so much of its outer hydrogen envelope that astronomers would have classified it, had anyone been able to observe it up close, as a Wolf-Rayet star, a name for hot, stripped-down stars that have blown away the hydrogen-rich material they were born with, and now show their hotter, more processed inner layers directly to space. A Wolf-Rayet star is smaller, hotter, and far more violent at its surface than the star that formed it. It is already a star partway toward its own death, well before that final second arrives. The removal of that outer envelope matters enormously for what happens next, because a bare, stripped star behaves very differently when its core finally fails than one still wrapped in a thick blanket of hydrogen. Without a massive envelope to punch through, anything that erupts from the core afterward has a far easier path outward. Nothing about this was visible from the outside as anything other than a hot, bright, wind-driven star. There was no warning sign, no dimming, no obvious countdown. The clock that mattered was running silently at the very center, inside a core of iron that grew heavier and denser with every passing year, edging toward a limit that no core of iron can survive. That limit is set by a strange rule from quantum physics. Even in a core so dense that electrons are jammed against one another, a form of pressure called electron degeneracy pressure can still hold the core up, resisting further collapse simply because two electrons cannot occupy the same state at the same place. It is a strange, almost stubborn kind of support, unrelated to heat or fusion, and for a while it is enough. But it has a ceiling. Once the iron core's mass climbs past roughly 1.5 times the mass of the Sun, electron degeneracy pressure can no longer hold the weight above it, no matter how hard the electrons resist. For this star, built from something like 40 solar masses to begin with, that threshold was only ever a matter of time. By the final day of its existence, the star's core had grown to that critical mass, sitting at the center of a body that, from the outside, still looked like an ordinary hot star embedded in space. It had no way to know what it was approaching. There was no last flare, no final warning shot. The core simply kept growing, one fusion shell at a time, iron ash falling steadily inward until it crossed a line that physics does not allow any structure of that composition to cross and remain standing. To grasp the scale of a star like this, it helps to picture the sun shrunk to the size of a marble. On that scale, this star would have started out as a grapefruit, some 40 times heavier than the marble despite being only modestly larger across. Because its interior ran at pressures and temperatures the sun's core will never reach, and the galaxy holding it sat far enough away that the light leaving its surface that final day would not arrive at Earth for close to 2 billion years, more time than complex. Multicellular life had yet existed anywhere on Earth when that light began its journey. Inside that iron core, one process was about to unfold in under a second, and it would end with this quietly dying star becoming the source of the brightest flash of gamma rays ever recorded reaching Earth. The iron core that had been quietly growing at the center of the dying star for years finally crossed its breaking point, and everything that followed happened faster than anything astronomers can fully picture. Electron degeneracy pressure, the quantum standoff that had held the core up until now, gave way all at once, and the core began to collapse under its own gravity. What happened next took well under a second. In that instant, the core imploded from something wider than Earth into an object only a few dozen kilometers across, falling inward at a meaningful fraction of the speed of light. As the collapsing material was crushed together, protons and electrons were forced to combine into neutrons, releasing a colossal burst of ghostly particles called neutrinos, particles so unwilling to interact with ordinary matter that the vast majority sailed straight out through the star's remaining layers, as though they were not there at all, carrying away most of the energy of the collapse in the process. For a star of more modest mass, this collapse would stop there, leaving behind a neutron star, an object so dense that a teaspoon of its material would outweigh a mountain, held up by a new form of degeneracy pressure among the neutrons themselves. But this star's core had too much mass falling onto it. The rebounding shock wave that, in a smaller star, blows the outer layers away in a supernova explosion here, struggled against an enormous continuing rain of infalling material, matter still plunging down from the shells of unburned fuel above. Current models of very massive, hydrogen-poor stars like this one predict that the neutron star forming at the center could not stay a neutron star for long. Matter kept falling onto it, adding mass faster than even neutron degeneracy pressure could resist, and within seconds it likely crossed its own limit and collapsed one step further into a black hole, an object whose gravity is so extreme that nothing, not even light, can escape from within a boundary called the event horizon. This entire sequence, from a massive star's iron core to a newborn black hole, is what astronomers call the collapsar model, and it is currently the leading explanation for the kind of long-lasting gamma-ray burst this star produced. It is worth pausing on how strange this really is. A structure that had taken millions of years to build, layer by layer, converted itself into an object with an event horizon only kilometers across in less time than it takes to read this sentence aloud. To put that collapse in scale, imagine Earth, roughly 12,742 kilometers across, shrinking to the width of a small city in under a second, and then continuing to shrink from there until what is left could sit inside a modest office building. That is roughly the transformation the star's core underwent. A core collapsing to a point no wider than a city, in under a second, compressed into an interval of time too short for a human eye to register as anything other than instantaneous. The black hole did not form in isolation. Because the collapsing core was almost certainly spinning, material could not fall directly in from every direction at once. Instead, infalling gas flattened into a swirling superheated disk around the newly formed black hole, called an accretion disk, spiraling inward while colliding with itself and releasing tremendous amounts of energy as heat and radiation before finally crossing the event horizon. This disk, and the intense, twisted magnetic fields threading through it, would turn out to be the engine behind everything that happened next, channeling a fraction of that infalling energy into two narrow jets of matter, blasted outward along the black hole's spin axis, straight through what remained of the collapsing star above. None of this was visible to any observer at the time, because none of it had yet produced light that could escape the star. The star's outer layers, thinned as they were after years of fierce stellar winds, were still physically in the way, an obstacle the newly formed jets would have to punch through before the universe outside would learn that anything had happened at all. Nearly all the energy released by this collapse, more than 99% of it, by most estimates for a core collapse of this kind, left immediately as that flood of neutrinos, invisible and undetected from this particular event, already through Earth and gone within minutes of being produced, roughly 2 billion years before Earth itself would feel any part of what remained. What eventually reached telescopes on Earth, the gamma rays that would make headlines 2 billion years later, came from only a sliver of the energy budget of that single second, the sliver that found its way into the jets now forming at the black hole's poles. Those jets, still trapped inside the collapsing outer layers of the star, had one task left before any of this could become visible from the outside, burrowing through tens of thousands of kilometers of stellar material fast enough to escape before losing all their energy to the collision. The two jets now driving outward from the region around the newborn black hole carried only a small fraction of the collapse's total energy, but concentrated into an almost impossibly narrow beam, that fraction was enough to briefly outshine every other source of gamma rays in the observable universe. Powered by the twisting magnetic fields threading the accretion disk and by energy drawn from the black hole's own rotation through a process theorists describe with a set of equations from general relativity, the jets accelerated material outward along the black hole's spin axis to speeds almost indistinguishable from the speed of light itself. Physicists describe how close something gets to light speed using a number called the Lorentz factor, a measure of how strongly an object's own sense of time and distance is warped relative to an observer watching from outside. A Lorentz factor of 1 means an object is at rest. A Lorentz factor of 10 means, roughly, that a clock on that object appears to a stationary observer to be ticking 10 times slower than usual, and that the object appears compressed into a tenth of its length along its direction of motion. The jets in gamma-ray bursts like this one are estimated to reach Lorentz factors in the hundreds, meaning the material inside them was moving at more than 99.99% of the speed of light, so close to the ultimate speed limit of the universe that the difference from light itself becomes vanishingly small. To put that speed in perspective, if this material and a beam of light both raced from New York to Los Angeles, a distance light itself crosses in about 13 thousandths of a second, the jet material would fall behind by a gap too small for any instrument built before the 20th century to have measured. Material moving that fast does something unusual to the light it emits. Rather than radiating in every direction the way an ordinary hot object does, it beams almost all of its radiation forward into an extremely narrow cone in its own direction of travel, an effect called relativistic beaming. The faster the material moves, the narrower that cone becomes. For a jet with a Lorentz factor of several hundred, the beam of radiation can be confined to an angle only a few degrees wide, a needle of light rather than a floodlight. This detail turns out to matter enormously for who, anywhere in the universe, would ever get to see this event at all. Before any of that light could reach open space, though, the jets first had to fight their way out through the collapsing star itself. The star's remaining envelope, thinned by years of mass loss but still present, closed in around the jet as it drilled outward, and for a time the jet's leading edge behaved less like a beam of light escaping, and more like a drill bit forcing its way through rock, depositing enormous amounts of energy into the surrounding stellar material and inflating a hot, high-pressure bubble called a cocoon around itself. Only once the jet had bored all the way through the star's outer layers, a journey that current models estimate took a matter of seconds even at close to light speed, could it finally break free into open space and begin radiating its gamma rays outward unobstructed into the surrounding universe. The moment a jet like this breaks out from the surface of its dying star is the moment a long gamma ray burst actually begins in the sense. Astronomers on Earth would recognize a sudden, chaotic flood of gamma-ray photons produced as faster-moving material inside the jet slams into slower-moving material ahead of it, in a process called internal shocks. Each collision converts a portion of the jet's enormous kinetic energy directly into gamma rays, the most energetic form of light there is, thousands of times more energetic per photon than the light our eyes can see. For this particular star, that process did not last mere seconds as it does for many gamma-ray bursts. The main flood of gamma rays continued, in bursts and pulses, for roughly 300 seconds, well over 5 minutes of continuous emission, unusually long-lived even by the standards of long gamma-ray bursts, most of which finish within under a minute. That extended, furious engine is part of why, when this particular beam happened to be pointed at the right patch of sky, it would end up dwarfing every gamma-ray burst humanity had ever recorded, but only for an audience sitting almost perfectly on the beam's narrow axis. By the time the jet's gamma rays broke free of the collapsing star, they were no longer spreading outward in every direction the way light from an ordinary explosion does. Relativistic beaming had already confined nearly all of that radiation into a beam of gamma rays no wider than a pencil point, aimed by chance straight at Earth, at least as it happened for our galaxy, though the jet itself had no target and no aim in any deliberate sense. It simply followed the black hole's spin axis, wherever that axis happened to be pointing. This detail changes everything about how gamma-ray bursts are seen from Earth. And it explains something astronomers had puzzled over. Since the first bursts were detected by military satellites decades ago, built originally to watch for clandestine nuclear tests rather than for the cosmos, if a jet's beam is only a few degrees wide, then only observers sitting almost exactly along that narrow cone will ever see the burst as a burst at all. Widen the angle by even a modest amount, and the same explosion would appear far fainter, or would not register as a distinct event at all, its gamma rays never crossing an observer's line of sight with any useful intensity. Astronomers now estimate that for every long gamma ray burst, whose jet happens to point at Earth closely enough to be recorded, there may be dozens or even hundreds of similar explosions happening elsewhere in the universe, whose jets are simply pointed the wrong way. Invisible to us not because they are fainter, but because we are standing outside their beam entirely. Gamma-ray bursts themselves were only discovered by accident in the late 1960s when American Vela satellites, launched to watch for secret nuclear weapons tests in violation of a newly signed treaty banning atmospheric detonations, began registering flashes of gamma rays that were clearly not coming from Earth at all. It took nearly a decade of quiet analysis before the scientific community accepted that these flashes were coming from deep space, and it took several decades more and the launch of dedicated space telescopes built specifically to study them, before astronomers settled on the LHAASO model as the likely explanation for the longer class of these bursts. That history matters here, because it explains why an event like this one, however common the underlying physics might be across the universe, still counts as rare from Earth's point of view. Humanity has only been capable of recognizing a gamma-ray burst for a little over half a century. A narrow sliver of time set against roughly one event of this kind occurring somewhere in the observable universe on most days. That makes the star's death on its own an unremarkable event by the standards of the universe. Massive, stripped stars collapse into black holes and launch gamma-ray jets somewhere in the observable universe on a regular basis, likely close to once a day when counted across the whole of it. What made this particular collapse worth naming, worth remembering, worth building years of follow-up observations around, was not the physics of the explosion itself, which followed the same collapsar process astronomers had already modelled for other long gamma-ray bursts. It was the coincidence of geometry. This star's spin axis happened to point close enough to Earth's direction that its narrow beam of gamma rays swept directly across the location our planet would later occupy, roughly 2 billion years after the fact. Coincidence alone does not explain the burst's astonishing brightness, though a second factor mattered just as much: distance. Many long gamma-ray bursts detected by orbiting instruments come from galaxies far more distant than this one, their light stretched and dimmed by having crossed a much larger share of the observable universe before arriving. This particular burst's host galaxy, while still extremely far away by any human measure, sat closer to Earth than the great majority of gamma-ray bursts ever recorded. At a distance corresponding to a redshift of about 0.151, a measurement of how much the wavelength of the burst's light has been stretched by the universe's own expansion during the journey. A well-aimed beam and a comparatively nearby source turned out to be a rare combination, and this star's death delivered both at once. Astronomers sometimes describe this kind of alignment as winning a cosmic lottery, not because anything was drawn or chosen, but because the odds of any single observer sitting inside a random gamma-ray burst's narrow beam, from a source close enough to register as extraordinarily bright, are genuinely small. Multiply the odds of a favourable jet angle by the odds of a favourable distance, and events like this one, bright enough to threaten to saturate every gamma-ray detector watching the sky at once, are expected to reach Earth only rarely across the whole history of gamma-ray astronomy. The beam that would eventually strike Earth's detectors had, by this point in the story, already left its source and begun the long crossing between one galaxy and another, carrying the signature of everything that had happened inside that collapsing star. The shape of its jets, the duration of its central engine, and the precise angle of a spin axis set in motion long before the star itself had finished forming. That beam of gamma rays, and the visible and radio light produced alongside it, now had nothing left to do but travel, crossing a gulf of space so vast that its journey would outlast entire epochs of Earth's own history before it ever reached a single detector. This is the part of the story where the universe itself becomes a character. Light does not simply cross a fixed distance between two unmoving points, because the space between the source and the destination is itself expanding as the light travels through it. Cosmologists describe this stretching using redshift, a measurement of how much longer the light's wavelength has become by the time it arrives compared to when it was emitted, caused by the universe's own expansion carrying every point of space away from every other point during the crossing. For this burst, astronomers measured a redshift of about 0.151 once its light finally arrived, translating to a light travel time of roughly 2 billion years, meaning the gamma rays first captured by Earth's instruments in 2022 had been in transit since a period when Earth was in a very different chapter of its own history. Because space itself has continued expanding during that whole crossing, the galaxy that produced this light is not actually 2 billion light-years away today. It has continued to recede, carried outward by the universe's expansion, even while its ancient light kept travelling toward us, and current cosmological models place its present distance meaningfully farther than the distance implied by the light travel time alone. Both figures describe the same source. They are simply answers to two different questions, one about when the light left, and one about where its source has ended up since. To place 2 billion years on a scale a person can hold in mind, consider what was happening on Earth when this light began its journey. Complex, multicellular life was only beginning to establish itself in Earth's oceans around that time, single-celled organisms still dominating almost every environment on the planet. There were no plants on land, no animals of any kind, nothing resembling a forest, shell, or a bone anywhere on the surface of the Earth. The supercontinent arrangements familiar from later chapters of geology had not yet formed. The very outline of the planet's continents would have been unrecognizable. Across the entire span of time it took this light to cross the gap between one galaxy and another, Earth's oceans filled with increasingly complex life. Land was colonized first by plants and then by animals. Dinosaurs rose and were wiped out by an asteroid impact. Mammals diversified, and eventually a species capable of building gamma-ray detectors and pointing them at the sky arose, entirely unaware that a beam of light aimed roughly in its direction was already more than halfway through a journey that began before any of it had happened. That beam did not travel alone through empty, featureless space. As it crossed intervening galaxies and vast stretches of intergalactic gas and dust, it interacted in tiny but measurable ways with matter along its path, matter that would later help astronomers reconstruct details about the journey itself, including gas within our own galaxy that the light had to pass through in its very last moments before reaching any telescope. None of those interactions were enough to meaningfully weaken the burst's core signal. What began as one of the most energetic gamma-ray bursts a collapsing star has ever produced remained, even after 2 billion years of travel and cosmic expansion, bright enough to be an emergency the moment it finally arrived. It is worth returning here to a single photon crossing roughly 2 billion years of expanding space, one small packet of pure energy released in the final second of a massive star's life, surviving a journey longer than most stars themselves will ever live. Arriving finally at a small blue planet that did not exist as an ocean-covered world, let alone a world with observers, when that photon first set out. On October 9, 2022, that 2 billion year journey ended in the span of a few hundred seconds, all at once, on a planet whose instruments happened, this time, to be watching. In the early afternoon of October 9, 2022, Coordinated Universal Time, gamma rays from that 2 billion year old explosion began arriving at Earth, and within seconds, instruments on more than one spacecraft registered. Something had gone wrong with their own detectors, not because anything had failed, but because the signal arriving was so much stronger than anything their instruments were built to measure cleanly. NASA's Fermi Gamma Ray Space Telescope, carrying an instrument called the Gamma Ray Burst Monitor, recorded a spike so intense that its detectors briefly saturated, unable to accurately count individual gamma ray photons, because they were arriving faster than the electronics could process them, similar to a camera's sensor washing out completely when pointed directly at the sun. Within the same window, the Neil Gehrels Swift Observatory's Burst Alert Telescope registered the event as well, along with instruments aboard other spacecraft, including Russia's Conus Wind Detector and Chinus Jicam satellites, giving astronomers around the world a rare, near-simultaneous, multi-instrument record of the same extraordinary flash. Automated alerts went out within minutes through a system called the Gamma Ray Coordinates Network, which exists precisely so that when one instrument spots a burst, telescopes around the world, and in some cases in orbit, can swing toward the same patch of sky before the burst's afterglow fades. Astronomers who received those alerts recognized almost immediately, from the raw brightness figures alone, that this was not an ordinary gamma ray burst. Within hours, researchers were already using an informal nickname that would stick for the rest of the event's public life. The boat, short for Brightest Of All Time, a title no other confirmed gamma ray burst in more than 50 years of observation has come close to matching. Ground-based observatories joined the effort within hours as well. Optical telescopes across multiple continents, coordinated through the same alert network, swung toward the burst's coordinates as soon as local skies turned dark enough to observe, racing to capture the afterglow before it faded below what their instruments could detect. Some of the earliest ground-based images actually showed the afterglow saturating pixels on ordinary optical cameras, an echo of the same saturation problem that had affected the orbiting gamma ray detectors hours earlier, this time in visible light rather than gamma rays. Coordinating a response this fast, across telescopes owned by different institutions and different countries, depended entirely on the automated alert system built specifically for moments like this one, a piece of scientific infrastructure that exists for no other purpose than to be ready on the rare day an event this significant actually occurs. The burst's effects were not confined to instruments in space. Gamma rays and X-rays from the event, upon reaching Earth's upper atmosphere, deposited enough energy to measurably disturb the ionosphere, the electrically charged layer of Earth's atmosphere that begins roughly 60 kilometers up and plays a crucial role in how radio signals travel around the planet. Very low-frequency radio receivers on the ground, instruments normally used to study lightning and the ionosphere is ordinary daily behavior, recorded a sudden, sharp disturbance at the moment the burst's higher energy radiation arrived. A change in the ionosphere is electrical properties comparable in size to what a powerful solar flare from our own sun can produce, this time triggered by light from a source 2 billion light-years away, rather than a source 8 light-minutes away. It marked one of the only times a source from so far outside our own solar system has been shown to measurably affect Earth's atmosphere in a way ordinary monitoring equipment could pick up directly, without needing a dedicated gamma-ray telescope at all. None of this posed any danger. The burst's energy, spread out across the enormous distance it had to cross, arrived at Earth as an extraordinarily strong signal by the standards of gamma-ray astronomy, but nowhere near strong enough to threaten the atmosphere, the surface, or anything living on it. Had this same explosion occurred within our own galaxy, at a distance measured in thousands rather than billions of light-years, the outcome for any planet sitting near its beam could have been far more serious, potentially damaging the ozone layer of a nearby world enough to disrupt its ecosystem. But at 2 billion light-years, the burst's effects were an instrument testing curiosity and an atmospheric footnote, not a hazard. What made the day remarkable, in the end, was less any single measurement and more the sheer number of instruments, built across decades and by multiple countries for entirely different purposes, that happened to notice the same thing within minutes of one another. Gamma-ray satellites built to hunt for exactly this kind of event, radio receivers built to monitor lightning, and within days, optical and radio telescopes on the ground swinging toward the same coordinates to catch whatever light remained behind after the initial flash had passed. The burst that began with a dying star's core 2 billion years earlier had, in the space of a single October afternoon, become the most closely watched event in the short history of gamma-ray astronomy. Turning that flood of raw detector data into an actual measurement of just how bright the burst had been would take astronomers considerably longer than the burst itself had lasted. Working out exactly how bright this burst had been took astronomers weeks of careful analysis, because the raw detector readings from the moment of saturation were, ironically, the least useful data available. Instruments that have been overwhelmed cannot accurately count photons arriving faster than they can process. Researchers instead turned to secondary instruments that had recorded the event without saturating, along with the burst's later, fainter phases, and worked backward using established models of how gamma-ray bursts behave to reconstruct just how intense the peak had actually been. The measurement that matters most for comparing one burst to another is called fluence, the total amount of energy received per unit area at Earth, integrated across the whole duration of the burst. When astronomers finished their reconstruction, this burst's fluence came out roughly 10 times higher than the previous record holder, a burst detected in 2013, and tens of times brighter than the typical bright burst in the several-decade catalogue of gamma-ray bursts recorded since dedicated detectors began operating in the 1990s. Translating that fluence into the total energy the source itself must have released, assuming its radiation was distributed evenly in every direction, produces a number so large that astronomers describe it using a deliberately qualified term, isotropic equivalent energy, a bookkeeping figure that would represent the true energy output only if the burst had radiated equally in all directions, which, because of the narrow pencil point beaming of the jet, it almost certainly did not. That distinction matters. The actual energy carried by the jet itself, the true output of the collapsing star's central engine, is very likely a small fraction of the isotropic equivalent figure, because a beam of gamma rays no wider than a pencil point, aimed by chance straight at Earth, concentrates its true energy into an angle covering only a tiny sliver of the sky as seen from the source, rather than spreading it in every direction the isotropic equivalent calculation assumes. Even accounting for that correction though, the true energy released by the jet remains extraordinary by any standard, comparable to or exceeding the most energetic gamma-ray bursts previously catalogued, once the geometry of each burst's own beam is taken into account. Astronomers also compared this burst brightness to how often an event of this magnitude ought to occur at all, given everything known about the rate of gamma-ray bursts across the observable universe, and the narrow odds of any one of them being both close enough and well aimed enough to appear this bright from Earth. Several independent research groups arrived at similar conclusions. An event this intense, reaching Earth this clearly, is expected to occur, on average, somewhere between once every several hundred years and once every 10,000 years, depending on the details of the statistical model used. Put differently, gamma-ray astronomy itself, as a scientific discipline with working detectors in orbit, is barely 60 years old, and by pure chance, this instrument testing extreme happened to arrive during the narrow window in which humanity actually had the equipment pointed at the sky to notice. To build that comparison, researchers drew on a catalogue of several thousand gamma-ray bursts recorded since dedicated detectors began flying in the 1990s, ranking each by fluence and by the total energy inferred from its distance. Against that entire multi-decade catalogue, this burst did not simply edge out the previous record. It cleared it by a wide enough margin that several independent teams initially checked their own instruments for errors before accepting that the measurement was real, a natural response given how rarely any single measurement in astronomy stands so far outside the existing distribution of everything recorded before it. That rarity is precisely why the nickname stuck. Researchers are, by professional habit, cautious about superlatives, reluctant to declare any single measurement the biggest or brightest of anything without extensive caveats. But repeated independent reanalyses of this burst's data, across different instruments, different research groups, and different methods of reconstructing its true brightness, kept arriving at the same conclusion. Among every gamma-ray burst detected since the first satellites began watching for them, this one stood clearly apart, not by a narrow margin but by nearly an order of magnitude. Papers describing the event began appearing within months, and by the following year, the name boat had moved from an informal nickname exchanged between researchers into the term used in the scientific literature itself. The initial flash, though, was only the first act. What the burst left behind as its light faded would occupy telescopes on the ground for months afterward. Once the initial flood of gamma rays faded, the burst entered what astronomers call its afterglow phase, a longer-lived, gradually dimming glow produced not by the central engine itself but by the aftermath of its jet slamming into gas and dust in the space surrounding the dying star, in a process broadly similar to the internal shocks that produced the burst's original gamma rays, but now happening as the jet's outer edge collided with its surroundings rather than with itself. This afterglow radiates across almost the entire electromagnetic spectrum, moving from X-rays in the hours after the main burst, through visible light and infrared over the following days, and finally into radio wavelengths that can remain detectable for months or even years after the event itself. Much of this radiation across every one of those wavelengths is produced by a mechanism called synchrotron radiation, charged particles, mostly electrons, spiraling around magnetic field lines at close to the speed of light and radiating energy as they do so, in the same basic physical process on a vastly larger scale that produces radio emission in laboratory particle accelerators on Earth. Because the afterglow followed the same underlying physics astronomers had already modelled from decades of other gamma-ray bursts, it offered a way to test those models against an event bright enough to measure in unprecedented detail, tracking how the afterglow's brightness and colour evolved, hour by hour and then day by day, far more precisely than fainter bursts ever allow. One of the more unusual results to come from this follow-up campaign involved not the burst itself but dust much closer to home, inside our own galaxy. As X-rays from the burst's afterglow travelled the final stretch of their journey through the Milky Way, some of them scattered off small clouds of interstellar dust lying between Earth and the burst's direction, at a range of different distances along that line of sight. Because light scattered off a nearer dust cloud arrives at Earth slightly sooner, having taken a shorter detour, than light scattered off a more distant cloud. This scattering effect produces a set of expanding rings of X-ray light around the burst's position in the sky, each ring corresponding to a different dust cloud at a different distance. Visible only because a burst this astonishingly bright provided enough scattered light to trace rings that fainter bursts never produce clearly enough to see. NASA's Neil Gehrels Swift Observatory, using its X-ray telescope, captured this expanding ring structure directly, and astronomers used the rings changing size over time to measure the distances to several previously uncharted dust clouds within our own galaxy, an unusual, almost accidental byproduct of studying an explosion 2 billion light-years away. A burst that originated far outside the Milky Way ended up mapping structure inside it. It is a reminder that this event's importance was never confined to the story of one dying star. Its brightness turned it into a diagnostic tool useful for studying nearly everything its light happened to pass through on the way to Earth. Beyond the dust rings, the sheer signal strength of this particular afterglow gave researchers an unusually clean dataset for testing broader questions about how gamma-ray burst jets slow down and spread as they age, questions normally studied using the combined noisier data from many fainter bursts averaged together. A single burst this bright, tracked in this much detail across so many wavelengths, functions almost like a calibration standard for the entire field, a reference case against which fainter, more typical bursts can be compared for years afterward. Follow-up observations continued for months after the initial burst, as radio telescopes tracked the slowly fading afterglow, and researchers refined their models of the jet structure, its energy, and how it interacted with material around the dying star. Each new observation added detail to a picture already unusually complete for a gamma-ray burst. Astronomers could reconstruct, with more confidence than for almost any previous event of this kind, the shape of the jet, the density of gas surrounding the collapsing star, and the overall energy budget of the explosion. What remained less certain, and what astronomers turned to next, was a question the burst's brightness alone could not answer. Whether the supernova that a collapsing, massive star like this one should also have produced had actually happened, and if so, why it was proving so difficult to see. Long gamma-ray bursts produced by the collapsar process are expected to come paired with a particular kind of supernova, a type IC supernova, marking the violent disruption of the outer layers of the collapsing star as the shockwave and radioactive material from the collapse blast outward, distinct from the jet itself and visible mainly in ordinary visible light rather than gamma rays. For most long gamma-ray bursts close enough to study in detail, this accompanying supernova becomes visible within 1 to 3 weeks of the initial burst, brightening and fading in a way that matches decades of supernova observations, closely enough that astronomers treat the collapsar model as well tested. Given how extraordinarily bright and well studied this particular burst already was, researchers expected its supernova, if one existed, to be one of the most thoroughly observed in history. It was not, and the reason had nothing to do with the supernova itself. The burst's location in the sky placed its host galaxy at what astronomers call low galactic latitude, meaning the line of sight from Earth to that distant galaxy passes close to the flat disk of our own Milky Way, the region of our galaxy thickest with gas and dust. Interstellar dust does not just dim light passing through it, it dims different wavelengths unevenly, absorbing and scattering blue light far more effectively than red light, an effect astronomers call extinction. Looking toward this burst's location meant looking through an unusually dust-choked stretch of our own galaxy, on top of whatever dust existed within the host galaxy itself, and the combined effect dimmed the optical light from any supernova at that location dramatically. Far more than for a typical gamma-ray burst host seen through a clearer patch of sky. The practical result was that astronomers spent weeks searching for a supernova they had every theoretical reason to expect, using some of the most capable telescopes and instruments available, and kept coming up with results too faint and too ambiguous to confirm anything conclusively. It was the opposite problem from the burst itself, an event so bright it saturated detectors built to survive nuclear test monitoring, paired with a companion event so thoroughly obscured that even sensitive infrared observations, chosen specifically because infrared light penetrates dust far more effectively than visible light, only turned up a candidate signal well after the point where a supernova of ordinary brightness should have been unmistakable. When researchers did eventually identify a probable supernova at the burst's location, designated SN 2022W, it appeared fainter than the typical supernova associated with a long gamma-ray burst, a result consistent with, though not fully explained by, the heavy dust extinction along the line of sight. Some researchers have suggested the supernova may also have been intrinsically less luminous than average for this class of event, though separating an intrinsically faint supernova from one that only appears faint because of dust in front of it remains genuinely difficult with the data available, and the question was still being debated by researchers in the time after the event. What is not in doubt is that a supernova, some kind of explosive disruption of the star's outer layers, almost certainly still did accompany the collapse, because every other detail of the burst, its duration, its energy, its behavior, matched the collapsar model closely enough that researchers see little reason to doubt the basic picture. A massive stripped star, a core collapsing into a black hole, a pair of relativistic jets, and an accompanying explosion of the star's remaining material, all happening within the same violent sub-minute sequence roughly 2 billion years ago. The dust that obscured the supernova was never a challenge to that picture. It was simply an accident of geography, a coincidence of which direction in the sky this particular star happened to occupy relative to the thickest part of our own galaxy's disk, standing between Earth and an explosion that, in every other respect, delivered more detail to astronomers than almost any burst before it. With the supernova finally faintly confirmed, one further question remained open: exactly what kind of object the collapse had actually left behind at its center. Every gamma-ray burst of this kind ends with something left behind at the center of the wreckage, a compact object formed from whatever mass did not get blown outward in the supernova or channeled into the jets. For a collapsar of this scale, beginning from a stripped star of roughly 40 solar masses, the leading model points to a stellar mass black hole, likely several times the mass of the Sun, formed in the same under-a-second collapse described earlier, a core collapsing to a point no wider than a city in under a second, crossing from ordinary matter into an object defined entirely by its gravity and its spin. Confirming exactly what was left behind, though, is far harder than confirming that the collapse itself happened, because a black hole does not announce its own existence with light the way a still-glowing neutron star or an actively feeding black hole with a bright accretion disk can. Once its accretion disk finishes feeding whatever infalling material remains and settles into quiet inactivity, an isolated black hole at this distance is, for all practical purposes, invisible to every telescope currently in operation, detectable only through its gravitational influence on nearby matter or light, neither of which is available for an object sitting alone 2 billion light-years away, with no visible companion star or surrounding cluster to reveal its presence indirectly. A minority of researchers have raised an alternative possibility worth mentioning honestly, that instead of continuing to collapse all the way to a black hole, the compact remnant stabilized as a magnetar, an extraordinarily strongly magnetized neutron star, if the collapsing core's final mass and rotation happened to land just below the threshold needed to form a black hole rather than above it. Magnetars are already known to power a different, much fainter class of high-energy flare, and some researchers have proposed that especially long-lasting, unusually structured gamma-ray bursts could, in principle, be explained by a newly formed magnetar continuing to inject energy into its surroundings for longer than a black hole's collapsor engine typically would. For this particular burst, the currently available evidence points more strongly toward the standard collapsar and stellar mass black hole picture, given the scale of the progenitor star and the total energy released, but researchers have not ruled out a magnetar contribution to some part of the burst's unusually long duration, and the honest answer, for now, is that the identity of the exact object now sitting at the heart of that 2-billion-year-old explosion remains inferred from models rather than observed directly. What can be said with much more confidence is what that object is not doing now, and will not do for the remainder of its existence, actively producing gamma-ray bursts of its own. The extraordinary flash that reached Earth in 2022 was a one-time event, tied specifically to the collapse itself and the brief, furious period afterward when infalling materials still fed the jets. Whatever object now occupies that point in space, whether a quiet stellar mass black hole, or less likely a newly formed magnetar, has long since settled into a much less dramatic existence, its accretion disk long since consumed or dispersed, its immediate surroundings cleared by the very explosion that created it. What the object left behind represents matters as much as the object itself. A stellar mass black hole, formed from the compressed remains of a star, once 40 times heavier than the Sun, silently occupying a small patch of space in a galaxy whose light, save for this one extraordinary flash, human telescopes may never study in this much detail again. It is one among an enormous, largely uncounted population of stellar mass black holes, scattered throughout every galaxy massive enough to have formed stars like this one, distinguished from the rest of that population by nothing about its ongoing existence, only by the extraordinary 2-billion-year-old flash of light that happened, this one time, to reach a small blue planet whose inhabitants had by then finally built the instruments needed to notice it. That flash, though, had one more surprise waiting inside it, hiding in its highest energy photons, the ones capable of testing physics far beyond anything a laboratory on Earth can reach. Among the photons produced by this burst, a small number arrived carrying energies far beyond typical gamma rays, energies so extreme that only a handful of specialized observatories on Earth are equipped to detect them at all. The Large High-Altitude Air Shower Observatory, an instrument array built high in the mountains of Sichuan province in China, and known by the acronym LHAASO, recorded photons from this burst with energies reaching into the tera-electron-volt range, roughly 1 trillion times the energy of a single photon of visible light, among the highest energy photons ever attributed to a gamma-ray burst. Observatories like LHAASO do not detect these extremely high-energy photons directly. Instead, when a photon of this energy strikes Earth's atmosphere, it triggers a cascade of secondary particles called an air shower, a spray of countless lower energy particles produced as the original photon interacts with atomic nuclei in the air, all traveling downward together, fast enough to produce a faint, fleeting flash of light called Cherenkov radiation, a kind of optical shock wave produced whenever a charged particle moves through a medium faster than light itself can travel through that same medium. Ground-based detector arrays are built specifically to catch these brief cascades and work backward to reconstruct the energy and direction of the original photon that triggered them. The presence of photons at these energies raised an immediate scientific puzzle, because photons this energetic are expected to have a hard time surviving a journey of 2 billion light-years at all. Space between galaxies is not perfectly empty. It contains a faint background of visible and infrared light called the extragalactic background light, produced cumulatively by every star and galaxy that has ever shone, and a sufficiently energetic gamma-ray photon can collide with one of these background light photons and be annihilated in the collision, converting both into a pair of new particles and never completing its journey. Existing models of the extragalactic background light predicted that photons at the very highest energies detected from this burst should have had only a slim chance of surviving the full crossing without being absorbed this way. That some of them clearly did arrive intact prompted researchers to revisit those models, testing whether the background light is somewhat less dense than assumed, whether the burst's true energy output at these extreme energies was underestimated, or whether some combination of ordinary, known physics accounts for the observation once the calculation is redone carefully. Work on reconciling the observation with the models is ongoing, and no consensus explanation had fully settled the question as of the most recent published analyses. A more speculative line of research has used the very same high-energy photons to search for something considerably stranger. Tiny hints of new physics at the boundary between quantum mechanics and gravity, a regime no laboratory experiment on Earth can currently probe directly. Some theoretical frameworks attempting to unite quantum physics with gravity predict that the fabric of space itself might not be perfectly smooth at extraordinarily small scales, and that this graininess could cause photons of different energies, even if emitted at exactly the same instant from the same distant source, to arrive at a detector with a tiny, energy-dependent difference in travel time, an effect too small to notice over any distance achievable in a laboratory, but potentially measurable after a 2 billion year journey. Researchers compared the arrival times of this burst's highest and lowest energy photons looking for exactly this signature. No convincing evidence of it was found, which does not disprove the underlying theoretical idea, but does allow researchers to place a tighter constraint than before on how large any such effect could possibly be, narrowing the space in which such new physics, if it exists at all, would have to hide. None of this made the burst dangerous, nor did it point to any exotic new phenomenon confirmed rather than merely searched for. What it did was turn a single 2 billion year old stellar collapse into a natural laboratory more extreme than anything humans can construct, its photons carrying information not only about the star that produced them, but about the space they crossed to get here, tested against some of the most fundamental open questions in modern physics along the way. Taken together, every piece of this event, the collapsing core, the narrow jets, the 2 billion year crossing, and the flood of data it delivered to instruments built for entirely different purposes, describes something astronomers now believe happens only rarely enough to be called, without much exaggeration, a once-in-a-civilization event. Estimates vary depending on the statistical model used, but most researchers who have studied the burst's brightness place the expected recurrence of something this intense, reaching Earth this clearly, somewhere between once every few hundred years and once every 10,000 years. Human civilizations have existed, in any organized form, for roughly 10,000 years. It is entirely plausible that this was the single brightest gamma-ray burst to reach Earth across the whole span of recorded human history, and it happened to arrive during the narrow sliver of that history, barely 6 decades, in which humanity had built the instruments capable of noticing. That timing was not fate, and it was not aimed at anyone. A beam of gamma rays no wider than a pencil point, aimed by chance straight at Earth, carries no intention and no awareness of what, if anything, lies at the far end of its path. The star that produced it collapsed roughly 2 billion years ago for reasons that had nothing to do with Earth, following physics that plays out the same way in every corner of the universe massive enough to build stars like it. Hydrogen fusing to helium, helium fusing to heavier elements, a core collapsing to a point no wider than a city in under a second, and jets of matter blasted outward along whatever axis the dying star's spin happened to define. That this star's spin axis pointed close enough to a still-forming solar system, and close enough in distance for the resulting flash to arrive bright rather than merely detectable, was a coincidence measured in odds, not design. It is worth pausing on what that coincidence actually connects. 2 billion years ago, before animals, before plants, before anything resembling the world we know had taken shape on Earth, a massive star elsewhere in the universe reached the end of its life and released, in under a second, more energy than the Sun will produce across its entire 10 billion year lifetime. That energy set off across the universe in every direction its geometry allowed, most of it in directions that would never encounter another observer at all. One narrow beam, among countless others produced by similar deaths across the history of the universe, happened to cross the exact point in space and time that a small rocky planet, orbiting an ordinary star, would occupy roughly 2 billion years later. Along the way, that beam passed through and briefly illuminated dust inside our own galaxy, tracing rings of scattered light that helped map structure closer to home than the beam's own source. It disturbed the electrically charged edge of our planet's atmosphere. It carried photons energetic enough to test the graininess of space itself, and to briefly challenge decades-old models of how much light fills the space between galaxies. None of that required the star or the universe to know anything about Earth. What it required was simply enough time and enough of these events happening somewhere for the numbers eventually to align. The universe is old enough and violent enough that even genuinely rare coincidences of this kind eventually occur and eventually get noticed, provided an observer happens to be watching with the right instruments at the right moment. Gamma-ray astronomy is younger than most living scientists themselves. The fact that this particular alignment fell within that narrow window says less about the star than about extraordinary luck in the timing of human technological history. What remains at the far end of everything this burst set in motion is a black hole, likely several times the mass of the Sun, sitting quietly in a galaxy roughly 2 billion light-years away, its violent moment of formation long past, its accretion disk long consumed. It produces no further gamma-ray bursts, and it will very likely never be studied in this much detail again, not because it has become uninteresting, but because the specific coincidence that made it visible, a beam pointed almost exactly at Earth from a comparatively nearby source, cannot simply be repeated on demand. Astronomers will keep watching the sky for the next one, fully aware that the next burst, bright enough to earn a comparable nickname, could arrive tomorrow, or could be centuries away, because nothing about when it happens is tied to anything humanity does or wants. What this single event leaves behind beyond the papers, the models, and the maps of galactic dust it happened to produce as a side effect is a genuinely rare kind of confirmation that the extreme physics astronomers have spent decades modelling from a distance. The collapse of a dying star, the launch of jets moving at nearly the speed of light, the stretching of light across an expanding universe, all held up in exhaustive detail against the single brightest test case that physics has ever handed a waiting instrument. The universe did not do this for us. It simply did it, as it has done countless times before and will do countless times again. And on this one occasion, 2 billion years after the fact, something on Earth happened to be looking in the right direction to see it. What began roughly 2 billion years ago as an ordinary, if unusually massive, death among stars ended on a single October afternoon in 2022 as the brightest flash of light ever recorded reaching this planet from anywhere in the universe. Nothing about that outcome required anything special from the star itself, only the same collapse that plays out inside massive stripped stars throughout the universe, a core giving way, a black hole forming in under a second, and a narrow beam of light launched outward along whatever axis chance provided. What made it extraordinary was entirely a matter of geometry and distance, a beam that happened to point close enough to Earth from a source close enough to appear astonishingly bright, an alignment so unlikely that astronomers expect to see its equal perhaps once in every 10,000 years. For the small stretch of human history capable of building instruments to notice, that alignment arrived at exactly the right moment, carrying with it a supernova hidden behind dust, rings of scattered light mapping our own galaxy, and photons energetic enough to test the very structure of space. None of it was sent. All of it was simply released 2 billion years ago by a star that had no way of knowing anything would ever be there to receive it. And that in the end is what a universe this old and this vast quietly guarantees, that somewhere, eventually, light finds an audience.